Welcome to the Crazy Hat Chemist. So another video here in electrochemistry, and we're feeling kind of unbalanced, so let's get balanced. Here we go. Bam! So balancing electrochemical equations number 3. Balance the redox equation when dioxyvanadium ion reacts with zinc. Now most of you probably don't know this reaction, so this is just going to be popping this in here just like that, and now what we're going to do is balance this, okay? So we have VO2 1 plus zinc solid produces VO2 plus zinc ion. That's a 2 plus. So what we need to do is assign oxidation numbers for the reactants and the products, that is all elements in this entire equation. Now what we do know is that elements in their standard state are 0, and we know that oxygen ion is an 0 O with a 2 minus charge. So knowing that oxide ion is a 2 minus charge, we should be able to solve for the vanadium on both the reactant and the product side. So the vanadium on the reactant side is a 5 plus because the oxide ion is a 2 minus. Make sure that you can do that. The zinc that's a solid is an element in its standard state. So at standard conditions, zinc is a solid, and elements in their standard state have an oxidation number of 0. And then vanadium on the product side is based on oxide having a 2 minus charge, and there's one oxide, there's one vanadium, and there's an overall 2 plus charge on this, and vanadium is going to be a 4 plus. The oxide, of course, is the 2 minus. Then the zinc that's an ion is a 2 plus charge, and that's its oxidation number already right there. Now what we're going to do is we're going to find the two elements of which change in oxidation number. One is the vanadium, one is the zinc. Okay, the vanadium is going from a 5 plus to a 4 plus. That's a reduction in oxidation number. The zinc is going from a 0 to a 2. That's an increase in oxidation number, therefore that's oxidation. Now what we're going to do is write now that we have identified which one is undergoing oxidation, which one is undergoing reduction, we can write our two half reactions. So here's our first half reaction right here. Okay, and then our second half reaction is right here. Notice again what I'm doing is I'm staying consistent and keeping my vertical line where the separation between the reactants and the products is. That's where the arrow is. The arrows are vertically correlated to each other. Okay, and so now what we're going to do is we're going to balance this for mass for all elements except for oxygens and hydrogens. So we're going to take that reduction half reaction with the vanadium and oxygen in it, balance the vanadiums first. The vanadiums are already balanced. There's one on the reactant side, one on the product side. What is not balanced are the oxygens. There are 2 oxygens on the reactant side, 1 oxygen on the product side. So this is the first time that we've come across unbalanced oxygens. So what we need to do is for every unbalanced oxygen, we are going to add 1 water molecule, because for 1 water, you have 1 oxygen. So on the product side, we are going to add 1 water molecule, just like what I've done right there. Now what I've done is I've added hydrogens. So, and there aren't any hydrogens on the reactant side. I've just added 2 hydrogens because water is H2O. So I'm going to add hydrogen ions to the reactant side. And so I'm going to add an equivalent number of hydrogen ions as I have hydrogens on the product side. So that would be 2 hydrogen ions. Okay, so now I've balanced this for mass. Now I need to balance it for charge. So I'm going to take a look at the charge on the reactant side. So each hydrogen ion is a 1 plus charge, and there are 2 of them, so that's a total of 2 plus charge on the reactant side thus far. The VO2 1 plus has a 1 plus charge. So I had a 2 plus charge with the hydrogens. I'm going to add 1 more plus charge, and that's a 3 plus charge on the reactant side due to the VO2 1 plus. On the product side, I have a VO2 2 plus. So on the reactant side, there's a 3 plus. On the product side is a 2 plus. Okay, this is also a new case where I haven't had one side equal 0, but it doesn't matter. I am going to make both sides equal to the lower number. of the two choices of a 3 plus on the reactant side and a 2 plus on the product side. The lower number is the 2 plus. So I need both sides to equal a 2 plus in its charge, overall charge. In order to do that, I'm going to add electrons. So I'm going to add 1 electron to the reactant side to get an overall net charge on the reactant side of a 2 plus, which is equivalent to the overall 2 plus charge on the product side. So here is that electron right there. Excuse me. All right, so that top reduction half reaction is done. Now I'm going to work on the bottom half reaction. There's 1 zinc on the reactant side, 1 zinc on the product side. The zincs are balanced. There are no other elements, so the only thing I need to do now is balance for charge. On the reactant side is a 0 net charge. On the product side is a 2 plus charge. So the lower of those two charges is a 0. So I need both sides to equal 0. So I'm going to add electrons. Again, you can only add electrons, and I'm going to add 2 electrons to the product side so that both the reactant and the product side has a net charge of 0, and that's what I've done right here. Now you should see that the top reaction, that is a reduction half reaction, has 1 electron, and the bottom reaction, that is the oxidation half reaction, has 2 electrons. So I am going to multiply the top reaction by 2. When I multiply the top reaction by 2, I will get 2 electrons, and then I will have 2 electrons on both the reduction half reaction and the oxidation half reaction. So what I'm going to do is I am going to distribute that 2 over all the terms in the reduction half reaction. So I'm going to cross this one out right there like I've done it, and rewrite it, but after having distributed that 2. Okay, and there it is right there. Now I'm going to draw a line in the sand such that I can add up these reactions, and you can only add up the reactions once the electrons on both the reactant and product side will cancel out. That is, you have an equivalent number of electrons on both the reactant and the product side. Then you can finally add and sum up the 2 reduction and oxidation half reactions. So it just so happens that there are 2 electrons on the reactant and product side, respectively, and those cancel out. Are there any other things that I can, combine or reduce or anything like that? No, there isn't. So I'm going to drop everything down and put the states of matter in there. And then this is the equation that I have. So now, this very last step here, before I start adding labels to everything, this very last step is to do a check to make sure that you have the correct charges and the correct mass on both the reactant and the product side. That's very critical. So let's take a look at the reactant side. In terms of hydrogens, I have 4 hydrogens on the reactant side. On the product side, I have 2 times water, which has 2 hydrogens in it, so it's 2 times 2 hydrogens. So the hydrogens are balanced. Then the vanadiums on the reactant side. I have 2 vanadiums on the reactant side. On the product side, I have 2 vanadiums. On the reactant side, I have 4 oxygens. That's 2 times 2, that's 4 oxygens. Okay, and on the product side, I have 2 oxygens in the VO2 plus, and I have 2 waters, and I'm going to sum those 2 up, and that gives me 4 oxygens. So the number of oxygens are now balanced. Then the zinc. I have 1 zinc on the reactant side, 1 zinc on the product side. So I am actually balanced for mass right now. Now I need to verify that I've balanced it for charge in addition to this. So with the 4 hydrogen ions, that's a 4 plus charge. The VO2 1 plus, there's 2 of those, that's a 2 plus charge. That's a total of a 6 plus charge on the reactant side. Okay, and then on the product side, I have a zinc that's a 2 plus charge. And there are the VO2 plus, there's 2 of those. So that's a total of a 4 plus charge with the addition of the zinc that's a 2 plus, that's a 6 plus charge. So I have also verified that there's a 6 plus charge on the reactant side, a 6 plus charge on the product side. So this is balanced for mass and it's balanced for charge, and I've verified both of those. Now I can label some things. So because there's an excess of hydrogen ion, or there's hydrogen ions in this reaction, that means that this reaction is occurring in an acidic solution. Sometimes this is denoted in the initial problem. I didn't let you know at the beginning of this problem that that was the case. But if there is additional hydrogen ions, then that means that this is in an acidic solution. So this is most certainly in acid. Doesn't matter if it's on the reactant or the product side, that extra hydrogen ions will let you know that it is in an acid solution. Furthermore, we can label what is the reduction, what's in the oxidation half reaction. Remember, this is always in relationship to the reactant side. You can never label the products. So the reduction portion of it is that vanadium, and the oxidation portion is the zinc. Remember, reduction is oxidizing agent. Those are really one and the same thing. Oxidation is the reducing agent. That is also one and the same thing. So now I've successfully balanced this equation for mass and for charge. And I want you to look at that balanced equation that's in the yellow. I don't see how you could have balanced that equation successfully without a lot of torture and pain by doing this another method. This half reaction, the half cell reaction method works very nicely. It's very difficult to balance electrochemical reactions or redox reactions that are in acid or in base by doing them by the old method of balancing equations, and that's just not possible with redox reactions unless you have tons of time on your hand and you're really bored. But we're not, because we have many other problems to do and many other things to do. Okay, I am the crazy hat chemist. I do have a crazy hat for you, and it is an octopus, of course. It has 8 legs. Hopefully you can see all 8 legs. If you enjoyed that video, I would appreciate you giving me a thumbs up. If you enjoy all of my videos, then please subscribe to my YouTube channel. If you know anybody else that's in a colleague of yours that's in a chemistry class with you, then please let them know about my videos as well. Pass on my videos to them. Hopefully they will benefit from them as well. You can find me and my website online, and you can donate and get yourself a sticker or even a t-shirt. I hope you have a fantastic day, and I will be teaching you more cool chemistry concepts next time. Bye for now.